Welcome to the Math Show Skill Drills with Mr. DeClerico. Last time on the Math Show with Mr. DeClerico, we talked about the work of John Napier and his discovery of the logarithm. However, a fact that often gets lost in the sauce is that Napier only used logarithms as a computational tool. The gentleman to give logarithms the dignity of being a function in their own right, and specifically an inverse function for an exponential, is this guy, Leonhard Euler, whose name I'm not going to try to pronounce in German. Today, we're going to talk about the properties of logarithms as functions in their own right. The first law of logarithms we're going to discuss is the product to sum or sum to product law. It goes like this. Log base a of x times y equals log base a of x plus log base a of y. Strange, but true. For example, log base 2 of 3 times x equals log base 2 of 3 plus log base 2 of x. The log of the product is equal to the sum of the logs. Now, if you're like Mr. Platypus, you want to know why this is true. So I'm going to have to issue a nerd alert. The proof for this law of logarithms is very, very nerdy. So buckle up your seatbelts. Here we go. All right, let's get to work. We're going to let u equal log base a of x and v equal log base a of y. This means, representing both of these equations as exponential equations, a to the u equals x and a to the v equals y. If you're not sure why we're allowed to do that, refer to my last video, which I left in the description. Then x times y equals a to the u times a to the v. That's just a little substitution. Using some properties of powers, a to the u times a to the v equals a to the u plus v. Power times power, add the exponents. I'm going to apply a logarithm to both sides of the equation, xy equals a to the u plus v. If I do, I get log base a of a to the u plus v. That allows us to use an inverse property of logarithms, which would yield u plus v. Again, if you're not sure why we were able to do that, refer to the video in the description. Doing a little substitution, we obtain log base a of x times y equals u plus v. Well, what are u and v? Well, let's go to the top. U equals log base a of x, and v equals log base a of y. So with a little substitution, I get my sum to product or product to sum property of logs. The next two properties of logs we'll discuss are corollaries of this one. What's a corollary? Well, Mr. Platypus can help us out with that. It's just a result that immediately follows a theorem. The next law of logarithms we're going to discuss is the quotient to difference or difference to quotient law. It reads, log base a of x divided by y equals log base a of x minus log base a of y. The log of the quotient equals the difference of the logs. For example, log base 2 of 3 over x equals log base 2 of 3 minus log base 2 of x. Finally, we have the exponent to coefficient law, or coefficient to exponent law. It reads like this. Log base a of b to the n equals n times log base a of b. This is the coolest property of logarithms, in my humble opinion. For example, log base 2 of y cubed equals 3 log base 2 of y. Notice, whatever my exponent is, that becomes a coefficient. And if I started with the right-hand side, this coefficient outside of the logarithm could become an exponent inside the logarithm. Sometimes in math, it's helpful to expand logarithmic expressions. That is, to take a logarithm with a lot going on inside and spread it out across a couple of terms, separated by addition and subtraction. Here's how we do it. We follow order of operations backwards. We turn division inside the logarithm into subtraction outside the logarithm. Then we turn multiplication inside the logarithm to addition outside the logarithm. And finally, we turn exponents inside the logarithm into coefficients outside the logarithm. Let's apply that set of rules to log base 3 of 8 over 5x squared. First thing we're going to do is we are going to turn division inside the logarithm into subtraction outside the logarithm. We would get log base 3 of 8 minus log base 3 of 5x squared. Now we're going to have to deal with this mess of 5x squared inside log base 3. Here's how we'll do it. We're going to turn multiplication 5 times x squared into a sum. Log base 3 of 5 plus log base 3 of x squared. Now we see we have an exponent, which we can turn into a coefficient. That would leave us log base 3 of 8 minus quantity log base 3 of 5 plus 2 as a coefficient log base 3 of x. Which is the answer? Though you may distribute this negative sign, as it were, into my two-termed expression into the parentheses, if you would so choose. Now try this one on your own. Feel free to pause the video and give it a go. Remember, proceed in order of operations backwards. Okay, I'll assume we're ready to continue. First thing we would do is we would turn the division inside the logarithm into a bit of subtraction. Then we would handle what's inside natural log, which is first going to be a product, which can turn into a sum, and then we handle the exponent of y and make it a coefficient. And we have our answer. Now we're going to talk about how to condense a logarithmic expression, which means to take a several-term long logarithmic expression and bring it all together into one logarithmic term. To do this, we're going to follow order of operations. We're going to take our coefficients and make them exponents, then turn addition into multiplication and subtraction into division in left to right order. That's very important. If you don't go from left to right order, you're going to come up with a different answer that is not correct. So, first thing we're going to do is look at this 2 that's a coefficient, and you can make that an exponent. Technically, you can make a negative 2 the exponent, and you'll get the right answer. But I'm going to stick with the positive 2 for simplicity's sake. Next, what you would do is you would turn this subtraction into division within the logarithm. Notice, I'm going from left to right, so I'm going to handle the subtraction first before I handle the addition. Finally, I'm going to turn the addition outside the logarithms into multiplication within the logarithm, in which I would get my answer. Here's one for you to try on your own. Feel free to give this one a go. Remember, once you deal with the exponents, go with order of operations, which means you're going to handle whatever's in the parentheses first. All right, I'll assume we're ready to continue. First, what we're going to do is deal with those exponents, that 3 at the front and that 2 within the parentheses. Then we're going to turn this addition right here into multiplication. Then we are going to turn the subtraction into division. Remember, need to follow order of operations, so parentheses come first. And there's your answer. Now here are some problems for you to try on your own. Feel free to pause the video, expand my first logarithmic expression, and condense the second logarithmic expression. Okay, I'll assume we're ready to continue. The expansion of the first logarithmic expression is what just appeared. And the condensation, if you will, of my second logarithmic expression is this one-termed expression I just put up. One more law of logarithms to keep in your back pocket is the change of base rule. It goes like this. Log base a of x is equal to common log of x over common log of a, which is equal to natural log of x over natural log of a, which equals log base whatever of x over log base that same whatever of a. Now, why is changing our base useful? Well, with very simple or old-fashioned calculators, they can only use common and natural log. So taking a logarithm with a base of not 10 or e and expressing it in terms of base 10 or base e is really helpful and sometimes necessary. Another question that arises is, well, why does this even work? Well, if you're here with Mr. Platypus, I'm going to have to issue another nerd alert, because we have another big messy proof on our hands that's going to be just as fun as the last one. Our first step is to let u be equal to log base a of x, which means if we convert that logarithmic equation into an exponential equation, we get a to the u equals x. That means I can apply a log base b, read different than base a, on both sides of that exponential equation. Then I'm going to use the coolest law of logs, in my humble opinion, to make that exponent of u a coefficient of the logarithm on the left. Then I'm going to divide both sides by log base b of a. And then, at long last, I'm going to remember that u is equal to log base a of x. So I can substitute log base a of x. And there you have it. Log base a of x equals log base whatever I want of x over log base that same whatever I want of a. I have changed my base. Now let's apply our knowledge. We're going to represent log base 4 of 6 as a ratio of common logs and as a ratio of natural logs. You can see what my response is, but feel free to try this one on your own if you'd like. Pause the video and give it a go. All right, I'll assume we're ready to continue either way. The ratio of common logs would be log of 6 over log of 4. Ratio of natural logs would be ln 6 over ln 4. If you can take any logarithm and express it as a ratio of common logs or natural logs, an old school calculator like this will thank you mightily. That's all for today. I hope you enjoyed this episode of The Math Show. And if you're feeling what Mr. Platypus is feeling, check out my website in the description. And as always, be sure to click subscribe, hit the like button, and all that good stuff.